Hello everyone, my name is Paolo Costa and I'm a researcher in Microsoft Research in Cambridge. In this talk I'll give you a short overview on Project Sirius, in which we try to answer the question, can we build a nanosecond optical network at data center scale? I'm sure you're all familiar with the Moore's law for CPUs, but a similar trend also applies to electrical switches. Every 2 years we have a new switch chip that has twice the boundary for the previous generation at roughly the same power and cost. And this is great because it allows to grow the network capacity without significantly affecting the power and cost. However, there is now a growing concern in the industry for how long this nice trend can continue. And this is probably the worst time for this to happen because we are also observing a spike in traffic demand driven by the availability of new devices such as AI accelerator or GPUs that can process data in excess of 1 terabit per second. So we think that this is a great opportunity to take a step back and see if there are new technologies that are non-CMOS dependent that can provide a new growth curve as we move in a post-Moore's era. And we think that optical switching could be a very promising candidate. So how can we switch packets using light? There are different ways in which this can be achieved. The specific technology we use in our project is called wavelength switching. It's based on two key components. The first one is called AWGR. It's a completely passive component. There are no transistors or buffers. It's basically etching of glass. And it has this nice property like a prism that it can redirect the light based on its wavelength or color. For example, if we have wavelength red, it will redirect on port 1, and if we have wavelength green, it will redirect on port 2. So we can combine this with a fast tunable laser, which as the name suggests is a laser that can tune very fast from one wavelength to another. And so by simply changing the wavelength of the laser, we can change the destination of the packet without requiring any packet processing in the network. Our goal is to use this technology to build a flat optical network that can scale to tens of thousands of nodes. So we want to replace the hierarchy of switches that we have in the core of our networks today with our passive core and using tunable lasers at the edge. What are the benefits? Well, first of all, since we are removing all electrical switches and transceivers in the core of the network, we can achieve a much cheaper network with a low power consumption. Second, since we don't have any buffers or packet processing in the network, we can achieve ultra-low and predictable latency, effectively the speed of light. And finally, since we are reducing our dependency on CMOS, and since the core is passive and so it's bandwidth agnostic, we believe that this could be a future-proof solution as we move into a post-Moore's era. So how fast can we tune these lasers? Well, when we started the project in 2016, we were using off-the-shelf tunable lasers that were able to tune in about 1 millisecond. The challenge with this is that if we want to keep the overhead to about 1 millisecond, it means that the transmission slot needs to be 9 milliseconds, which as 100 gigabit per second is about 110 megabytes per slot. Now this might be okay if we want to reconfigure in between jobs, for example, but clearly it's not a great fit for data center traffic that can be very bursty. So we spent the next year in the project to really try to optimize this technology. And in the end, we were able to show a worst-case tuning time of less than 100 nanoseconds. Now, on the one hand, this was a great result. It was 4 orders of magnitude better than when we started. And we were also able to reduce the transmission slot to 900 nanoseconds. The problem was that at 100 gigabit, this was still 11 kilobytes, which is much bigger than the size of a packet today. And so this was the time in which we realized that if we really want to achieve packet level reconfiguration and go below the 100 nanosecond threshold, we need to fundamentally change the way in which we design tunable lasers. So we came up with a new design for achieving fast tunability. We implemented this onto a photonic chip that we got fabricated in external foundry. And using this, we were able to demonstrate sub-nanosecond tuning time between any wavelength to any wavelength. And this is great because it shows that we can now achieve, in principle, 9 nanosecond slots, which effectively means achieving a slot size of 100 bytes, which is very close to what you have today with electrical packet switches. Now, as you can imagine, this has been a long journey. So we first designed the chip in-house, then we got it fabricated in external foundry, then we got the chip back and we did die-level testing in our facilities in Cambridge, and then we got the chip package so we could integrate it in our test. Now, you can think at this point we are pretty much done, but in fact we are just at the beginning of our journey. Because the challenge is that having a fast optical switch is just the first step towards building a nanosecond optical network. But a big part of the challenge is how to build a system that can operate in such a very fine-grained time scale. And so we spend the rest of the project in really trying to design a system that was optimized for the nanosecond regime, and also to build a 4x4 prototype that effectively was able to demonstrate the feasibility of our idea. And we were able to show FPGA to FPGA traffic with an end-to-end reconfiguration latency of less than 4 nanoseconds. So why is it so hard to build a nanosecond optical network? The reason is that already when we moved from slow optical switches, say millisecond timescale, to microsecond timescale, there were a number of challenges that as community we had to solve, for example, scheduling or control plane. But now all this problem becomes much harder when you go to a nanosecond timescale. And on top of this, you also have new challenges that were not really critical in the millisecond or microsecond, but that now becomes absolutely crucial. For example, every time you switch from one destination to another, the receiver has to recover the clock of the new transmitter. And this is something that typically takes hundreds of nanoseconds. And so if you want to achieve nanosecond reconfiguration time, we need to reduce this by 2 orders of magnitude. And then the next challenge we have is that we only have 100 wavelengths, but we want to connect tens of thousands or hundreds of thousands of servers. So how we can achieve that? And then scheduling was already challenging in the microsecond world. In a nanosecond regime, it becomes extremely hard to the point that it might not even be possible. In fact, even if we had a schedule, that would be completely pointless unless we also have a time synchronization mechanism that enables to achieve nanosecond accuracy. And finally, since the physical parts of the network are changing every tenth of nanosecond, TCP will not have enough time to converge to the correct rate, and so we need a new congestion control mechanism that enables to cope with this fast-changing world. Now, you might be tempted to see each of these problems as completely disconnected from each other and also belonging to different communities. But in fact, what we show in the paper is that by co-designing the whole stack from the ground up, and also by taking advantage of the unique properties of the cloud environment, we were able to come up with a solution that was much more efficient and much simpler. Unfortunately, I don't have the time to discuss in detail how we solved each of these challenges. However, in the paper you can find more information on the design of our nanosecond tunable laser, as well as the mechanism that we used to achieve a CDR lock-in time of less than 600 picoseconds and the time synchronization with sub-nanosecond accuracy. We also discussed how we scale our basic building block to be able to connect hundreds of thousands of servers with just 100 wavelengths, and also our schedule-less design that uses a cyclic schedule as opposed to on-demand schedule to orchestrate transmission. And finally, also how our congestion control can ensure predictable latency for short flows and high throughput for long flows. And as I was mentioning before, this was made possible by the fact there were a lot of synergies between all these layers. For example, the cyclic nature of the scheduling made it possible to simplify the design of the fast tunable lasers as well as the CDR, but also together with the passive core in the network and the lack of retiming, we were able to simplify the design of time synchronization, which in turn also helped for the CDR and congestion control. And there were other examples of this that you can find in the paper. What really excites us about this technology, it has the potential to change the way in which we manage resources and we design applications in our data centers. So today, as an application, you are restricted to use only local resources due to the limitation in terms of bandwidth and latency as soon as you leave your rack. However, if we are successful in building a network that can provide homogeneous bandwidth and latency across the entire data center, what this means is that we can provide the illusion of a single pool of resources. And in fact, since we have a very fine-grained time synchronization, we can also consider this as a synchronous system. So think, for example, what you can do if you have thousands of FPGAs all belonging to the same clock domain. Okay, and on this positive note, I'm going to conclude. So I hope I convinced you that by co-designing the stack and by taking advantage of the cloud scenario, it's possible to build a nanosecond optical network at data center scale. You can find more information about this project as well as other projects that are looking at optics technology in the context of storage and compute on our webpage. And I'm now more than happy to take all your questions.
So thank you for playing the video. So I'm going in the order of upvotes, and an upvoted question is, any thoughts on how to achieve nanosecond reconfiguration for WANs in light of WAN-specific challenges, reconfiguration delays introduced by a cascade of amplifiers?
Okay, thanks a lot for this question. So on this one, perhaps I would refer to the last talk of the session, which is also from our lab, where they actually, the team looked at how you can achieve how you can actually use optical switching in the context of the WAN. Specifically in that case, they were not looking at nanosecond because the traffic across data center is a bit more predictable, so you don't really need to go to the packet level granularity. However, they did a lot of work to actually deal with the issues coming from reconfiguring the optical switch and having to deal with a sequence of amplifiers. So I think probably it might be better to wait for that talk and then ask that question, because I think the team has really done a lot of work in that area.
All right, that's a great answer and a great advertisement. What is the roadmap to implement the required new fast line protocols within the existing interconnection ecosystem?
Yeah, so this is
asking about the road.
Yeah, so this is the broader discussion, and first of all, I want to make sure that at the moment this is still like a research project. So we are engaging with product group in Azure, but at the moment this is still remains a research project. There are of course both technical as well as non-technical conversations. For example, should be something that we develop in house, as opposed to something we developed as part of the consortium in order to create a bigger ecosystem. And as you can imagine, these are long and broader discussions. So at the moment, it's hard to really give a concrete answer. So I think we are start working on this. At least we show the technical feasibility, and then of course there is a strategic and business discussion that is happening now.
I see. Okay, another upvoted question: what is the port count for nanosecond optical switches?
Sorry, what?
What is the port count?
Okay, sorry. Yeah, so typically today you can find off the shelf a WGR with 100 ports, 100 wavelength. In literature, there also been demonstrated prototypes with 500, and I think the one with the largest number is 1,000 port. Of course, in that case, was using a slightly smaller bandwidth, so I think it was 1,000 port for with 25 gigahertz. But for example, the one that we use in our prototype was 100 port, and this is something that can be found off the shelf.
Okay, this is a question that even I had. Are there still places and opportunities for in-network computing in this new world?
Yeah, it's a very good question. I think absolutely. In fact, maybe I can argue that it's going to be actually even more relevant in the sense that effectively by having a passive core, it means that yes, in the core of the network, we cannot have network computing because the core by definition is passive. On the other hand, what we are doing is that we are pushing all the buffers close to the application, and that means that there are even more opportunity to use application-specific logic to manage this buffer, to process these packets. So by bringing the buffers close to the application, we are effectively enabling much higher application visibility, and also potentially create opportunities for doing much more application-specific processing on these packets, as opposed to packets that are in the core of the network as today, on which is hard for the application to have visibility and let alone to do any meaningful processing.
All right, I think we're at 9:15, but I haven't been pinged, so I'm going to ask one more question. What is the strategy for time synchronization? I think this is a good segue.
Yeah, it's a very good question. So I'm going to give like a short answer just in terms of time, but then I'm more than happy to follow up in offline. And we also had some text in the paper that describes it. So the high-level intuition is that since the core is passive, it means that when one node communicates with another node, just by virtue of receiving the signal, it can immediately recover the clock of the other party, and so I can compare locally how my clock is doing and compare with the other clock. And then also, since we have this cyclic communication pattern, it means that every microsecond I have a chance to talk with everyone else. And so it means that effectively every microsecond I have a chance to synchronize my clock with everyone else in the system. And the big advantage of optical switching is that there are no retimers in the center of the network. And so when I receive the signal, it's not being retimed by multiple switches on the path, but it's exactly the signal, exactly the clock that the source has been using. And so this allows to keep all the clocks on all the nodes in sync.
Thanks, Paolo. So let's move to the next talk, and then there's lots of questions, Paolo. So please.
Yeah, I'll follow up on Slack.
Okay, thank you very much for the great talk. So I'll start with some questions on Zoom. Can you tell us more about how the servers need to change with this extremely small RTTs in the data center network?
Okay, thanks a lot, Dong. So it's a good question. Well, so you can either just leave the server as they are, and you take still advantage of the benefit, the fact that the network costs less and has a lower power consumption. But if you really want to take advantage of the low and ultra low and predictable latency, the idea is that you should probably remove the inefficiency that you have today in many workloads, because you still have to go to the software stack. And we are seeing this trend in general anyway, moving towards more hardware-assisted workloads. So for example, if you think scenarios like FPGAs or AI accelerators. And once you move in that world and you remove all the inefficiency of the stack, at that point, the network latency becomes very critical. And having a network like Sirius that provides potentially in the order of tens or hundreds of nanoseconds end-to-end propagation latency, because you don't have switches in the middle and it's a flat topology, I think can be really beneficial to really then at that point shrink the end-to-end latency from applications, from one application to the other.
Right. So interestingly enough, the second paper on RMA is an effort that tries to address the problem in reducing the host side latency.
Exactly.
So I have a question on the scale of the network that you have built. What's the current scale of Sirius, and what do you envision? So what's the actual limit in the scale that you can support?
Yes. So it depends what you mean by current. So currently, Sirius is a research project. So at the moment, we have prototype in the order of a few nodes that we use for testing this technology. In the paper, we show that there are two ways in which Sirius can be deployed. One by just directly interconnecting servers, and using this technology, you can achieve in the order of a few thousand servers. For example, we have an example to achieve 5,000 servers, and this would be, for example, the size of an AI cluster. So where you want effectively to have to connect GPUs for doing AI training or inference. Or another example could be, for example, for memory disaggregation. In this case, again, you can have a few thousand nodes. If you really want to scale to the size of the data center, in that case, we interconnect using top of the rack in order to achieve one order well, you need to increase the scale of the system. And in that case, we show in the paper that using the latest Tomahawk switches, potentially we can connect up to almost 800,000 servers, which will be more than enough to interconnect even the biggest of our data center at the moment.
That is great. So there's one question that's related to this question. For large data centers, what changes are required at the Tor electrical switch if you're doing hybrid, right? So that's a question from Slack.
Yes, very good question. So yeah, we discussed a bit of this in the paper. There are two main changes that needs to happen. So the first one is the ability to either take an external clock or the ability to modify the clock on the switch, the reference clock. This is because we need to have very fast time synchronization. So the protocol itself can run in the microcontroller, but we need the ability to change the clock, or to adjust it, or as I said, to bring an external clock. The second big change that we have to do is the fact that we need to maintain W, where W is the number of wavelengths, 5 OQs per output port, and then effectively have this ability of doing the TDMA between these ports. And then on top of this, the other two changes is the routing logic and the congestion control protocol. And we believe, we have not completed this work, but we believe that this could be done potentially just using P4.
I see, great. I think in answering the question, you actually laid out the path in terms of how this technology would evolve and eventually move into the data center. Okay, one last quick question. There's a question from Slack from, I guess, an in-network computing enthusiast. The question is there any place and opportunity for in-network computing in this new world?
Yes, I think this is a very good question, and this is one. So you would be tempted to say no because the core of the network is passive. But actually, I would argue that a technology like Sirius may actually network compute even more relevant, in the sense that by pushing the buffers closer to the application, it could be either on the server side or on the TOR, effectively allow to bring the packets closer to where the application sits. And then what it means is that it's enabled to have more customized application-specific logic that you can use to process the packet, process the buffers, for example, decide which packets to drop or where to reroute the packets in case of congestion. As opposed to today, where most of the packets are hidden in the core of the network, on which application doesn't have visibility, and as which it doesn't have the application context in order to make these choices. Well, instead of pushing all these packets to the edge, what we are doing is that we are providing more application visibility and also context for making these decisions.
Great. I think the answer is very exciting, and it's what the community would like to hear. Okay. Thank you, Paulo.
Okay. Thanks so much. Thanks so much for your question.